An introduction to computing. So aims and objectives for this session are to introduce some fundamentals of computing for bioinformatics, to look at some different aspects of computing, and to show you how the internet works. Bioinformatics really brings together two different disciplines of biologists and computer scientists into this one idea of bioinformatics. Now obviously biologists know about biology, computer scientists know about computer science, but a key feature of bringing these two disciplines together is that it really needs to feed back into the biology and produce tools and predictions that are useful to biologists. So, looking at computers and computer science, what do computers have to do? They must handle data structures, information retrieval. They must handle algorithms, in other words, how to solve a problem. And we have the important concept of software engineering, which is turning an algorithm into an actual piece of software that can be run on a computer. Another very important area is data mining and machine learning, and these two concepts are really quite closely linked in that using machine learning or artificial intelligence to make predictions also can be used in order to look at data and pull out important concepts within those data. Networking and data transfer. In other words, how do we connect computers together either locally or across the world and transfer data between them? Let's take a look at computers themselves and operating systems. So this is what computers used to look like back in the 1960s, 1970s. Really big boxes, kind of the size of washing machines. This lady here is carrying a disk pack and pulling out a drawer where this will sit. And these disk packs had the capacity of maybe a few megabytes of storage. So really the amount of miniaturization that we've had over the last few decades is quite incredible. This is a paper tape machine. Some years ago, around about the early 1990s, I was doing some work for the National Grid company, and they still had computers that were booted off paper tape like this, although really this wasn't a technology that was used widely after the 1970s. So what we're looking at here is a strip of paper tape which has holes punched in it, and those holes represent binary digits, so zeros or ones depending whether there's a hole there or not. This was another technology which was used in a similar way, punched cards, and in the 1960s certainly, and probably in the 70s, Clark's shoes always used to come with one of these punched cards in it. So instead of having a barcode on an item, you had a punched card to describe what it was. And here you're seeing basically holes being punched to represent binary digits in a similar sort of way to what we had in the paper tape. Early computers made use of RAM, so remember the distinction between the RAM, which is the memory that's used to store data while you're working on it and programs while they're running, compared with disk storage, which is where your data files are stored when you save them, where your programs are stored. So early computers used this form of RAM, which was known as core memory. So these things are maybe a couple of inches across, and when you zoom in on them, you can see that it's basically a network of wires going up and down, threaded through little donut-shaped cores, as they're called, of a ferrite material. And this could be used to kind of magnetize these ferrite rings, and that would store the information. So we still use the term core in computing with Unix-like operating systems, things like Linux. So if a program crashes, it does what's known as a core dump, which means that it saves the state of its memory so that you can analyze where it crashed. And that term core dump comes from these metal cores. So here we're moving on a little bit in time to the 1980s. So this was the sort of computer that was being used at that time for bioinformatics type work. This is a tape drive for storing large amounts of information, and these are floppy disks. So this one's 5 1/4 inches, this one's an 8-inch disk, and those were used for transporting and storing relatively small amounts of data, so less than a megabyte on one of these. But this is a more modern sort of computer, so let's have a look at what it contains inside. There's what's known as a motherboard. So this is a printed circuit board which all the other components plug into. We'll then have the actual CPU processor, which is what actually does the computing work, and that plugs into the motherboard. We'll have RAM memory. We will have a graphics card that will drive the screen, but these days is often used for computing purposes as well. There are lots of programs that can make use of the computing power of the graphics card in order to do parallel calculations. So this is often used in things like machine learning and molecular dynamics. We'll have some sort of network card to connect to the local area network, a sound card, hard disks, perhaps some sort of optical drive, CD-ROM or DVD, and maybe, although rarely these days, some sort of floppy disk drive. Now, this lot at the bottom, the peripheral cards there are often integrated onto the motherboard itself, particularly in lower end, cheaper computers. What about an operating system? What is an operating system? Well, basically it's a software interface between the user's software and the computer's hardware. It provides things like the low-level networking, various tools for handling files, handling users and security, things like passwords and so on. It may, and generally these days does, but doesn't have to, provide a graphical user interface, so a point-and-click mouse-driven interface. And it may include other non-essential bundled tools, in the case of Windows, things like the Edge browser for browsing the internet, but those really aren't part of the operating system itself. Now, there used to be lots and lots of different operating systems, and lots of these were essentially driven by the manufacturers of the computers. So DEC, the Digital Equipment Corporation, had its own operating system called VMS. Another company, ICL, had an operating system called VME, and so on. These days there are really only three operating systems: Windows, that's used on PCs, various variations of Unix, Linux, and BSD, which are all very, very similar to one another, but different implementations. And Mac OS or OS X for Apple computers, although in reality this is actually built on a Linux implementation, just with a very attractive graphical interface. Historically, people working in areas like zoology, working with DNA, working with phylogenies, used to use Mac computers or PCs. Whereas people working in areas like protein crystallography, protein sequence and structure, tended to use these much larger computers that we were looking at earlier, these mini or mainframe computers. And this sort of thing tended to be used by computer scientists as well. So that means now that largely people working in the zoology, DNA, phylogeny area have tended to use Mac OS or Windows, whereas people using doing crystallography, looking at protein sequence and structure, and computer scientists tend to prefer Linux. But these days, because the latest version of the Mac OS, OS X, is actually built on top of a Linux type operating system. It's actually something called BSD Unix that was used as a basis for it. Then that means that there's a bit of a crossover here now between these, and a lot of people working in this area like to use Mac computers as well. Let's look then at data storage. Obviously, we store data on a hard disk, but how do we structure those data? Well, I like to make this distinction, which you may have heard from me before, between a data bank and a database. So a data bank is simply a collection of data, normally in simple plain text files, without a fixed associated query tool. And that means you can use different query tools to search that data bank depending on what you need to do. These are separate applications and allow you to do specialist searches. For example, if you took a data set of protein sequences, you might want to search based on the protein sequence itself. You might want to search based on the name of the protein you're interested in. You might want to search based on, is it an enzyme and its substrate is something or other. So you would need different search tools to do those different types of searches. A database, on the other hand, is a structured collection of data hiding behind some fixed tool allowing it to be queried. Now that could be a relational database, which we'll come on to speak about in just a moment, or it could be some sort of fixed web interface. And there's no other way of accessing the data other than through those resources. So relational databases are a way of taking a set of data and structuring those data into tables. And there are lots of examples. The one that people are likely to be most familiar with is Microsoft Access, which is the extra member of the Microsoft Office package. SQL Server is Microsoft's kind of professional database. Oracle is a huge company. They have huge offices just outside Reading, and they produce probably the best known commercial database. And there are other commercial ones like Sybase. These last two, MySQL and PostgreSQL, are open source free software. So particularly in the academic communities, those tend to be the two that are most widely used. MySQL is particularly popular, but actually PostgreSQL is faster for more complex queries. It has more kind of optimization, which makes it better for dealing with very large data sets and for more complex data where you need to link lots of these tables together. So as I said, data are separated into tables, which can also be referred to as relations, and hence the name relational database. Good database design really requires very careful thought and planning, and a process called normalization. So normalization employs what's known as CODS rules. So a computer scientist called Cod came up with this set of rules for looking at a big data set and normalizing it, and we will come back to those sorts of ideas. The point of things like normalization really is to maintain data integrity, to make sure that there aren't errors, there isn't any duplication and that sort of thing. So just to give you an example of why that's important. Now, I have to say this has been fixed now. This search was done some years ago, but I did a search on the NCBI website for Escherichia coli. Now, down on the right here, these are three alternative possible spellings of Escherichia. This is the correct one, and these are sort of erroneous ones. So what I've done here is do a search with this first incorrect spelling, and still we find 1,300 hits in PubMed, 5,000 in GenBank, and so on, 30,000 in dbSNP. This clearly is a problem because obviously there are loads more references to these things if you use the right spelling. And this is where normalization can help. So I've made up a few entries here from Uniprot KB/Swissprot with an accession code, an identifier, a species name, and a protein name. So here I've used those three different possible spellings of Escherichia. And obviously if you searched for this spelling you'd find this hit, search for this spelling you'd find this hit, and so on. So one of the things that we try to do in normalization with CODS rules is to remove what should be a repeating column, because each of these items should be identical. So what we do instead is take this one table and split it into two separate tables. And that repeating text information goes into a table here, and the other table simply refers to an entry in that table by some sort of numeric identifier. This means then that the spelling used here is the correct spelling. We make sure that it's the correct spelling, and we only put it in once. So that has two effects. First of all, it avoids the potential spelling errors, and secondly, it reduces the amount of data in the database, because instead of having a long string of text each time, we just have a number that is stored in the database table and refers to this other table. SQL, structured query language, often referred to just as SQL, is a standard database query language that's used for populating database tables and for querying those tables. Unfortunately, most databases seem to extend or deviate from that standard. But those extensions and deviations are generally fairly minor, and there are usually ways of getting round it if you need to port your data from one database to another. So SQL provides you with 4 types of command. First of all, what's known as schema creation. In other words, commands that create the tables that you're going to store data in. Secondly, there are commands for inserting data into the database. Thirdly, there are commands for extracting data from the database. And finally, there are database management commands which allow you to do things like delete tables, add users, give them permissions to read and write to particular tables, and so on. So here's an example of a schema creation command, which is creating a table called species. We're then creating within that table a column called spec ID or species ID, which is an integer, and we're creating a column called name, which is a character string of up to 80 characters. Here's another one that would create the sequences table that we saw in that previous example, where we have some sort of identifier for the sequence, and we'll allow that to be a character string of up to 16 characters, an accession code, which is a character string of up to 24 characters, a species ID, which is an integer, and that is the place at which we join the 2 tables together. And then a name for the sequence, again a character string of up to 80 characters. So to insert something into the first of those 2 tables, the species table, we would say insert into species the values 1 and Escherichia coli. So that would create ourselves a table with a single entry for Escherichia coli. Second, we could do insert into the sequences table the accession code P03629, the identifier hex3 E. coli, and then the species ID 1, which links us across to this other species table, and then finally the name of the protein. And here we're entering another sequence into the sequences table, and finally a third one. Data extraction is done using the select command. So we can select the name from the species table where the species ID is 1. And the result of doing that would be that we extracted the name Escherichia coli. Now, that's all very well, but how do we join those 2 tables together? Well, we would say select a.id, a.ac, b.name, a.name. Now, what we've done here is use A as an abbreviation for the sequences table and B as an abbreviation for the species table. So we're saying we're going to extract from these 2 tables, sequences A and species B. We're going to pull out the identifier, the accession and the name from the sequences table, and we're going to pull out the name from the species table. And then we say where a.specid equals b.specid. So we're only going to pull out things from those 2 tables where the species ID is the same. And that was that number 1 that we used to indicate that we were looking at E. coli. So this where statement acts to join the 2 tables together. And here's the results from doing that. We recreate that original table that we had, where we had the repeating information, but this time we're ensuring that we don't have any spelling errors. We're maintaining data integrity by joining the 2 tables together and actually only having that piece of text, Escherichia coli, in that second species table. Don't worry too much if you didn't follow that in too much detail, because we will come back to this in the second lecture on computing. Then the last type of command, as I said, for SQL is database management commands. So in this example, I'm granting select permission, in other words, the ability to query the table on the species table to public. That means to everybody. At that stage, we're going to take a break, and in part 2, we will look at algorithms, software engineering, machine learning, and the web.